Hi Jed, so today we're going to now go to 4.3 on proving triangles with the SSS. So in geometry or in just general trigonometry, one of the most important theorems when it comes to triangles will be the SSS. Well, not theorem, but postulate. And it'll be used a lot when you prove things. So it's just know that this chapter was really important, and especially this section. So postulate 19 or the SSS, side, congruence postulate, is kind of pretty self-explanatory by side. It means that if three sides of a triangle are congruent to three sides of another triangle, then the two triangles are congruent. I think this is pretty self-explanatory, but what something you have to remember is that this is a postulate, not a theorem. That has a really big impact on a lot of your calculations and what your proofs later on when you do geometry. I really think that this is pretty self-explanatory, but if you want to just look at maybe like this, for example, let's look at number 18, determine whether ABC is congruent to DEF. If they're congruent, write a congruent statement. So remember that they must have the same sides and it must be corresponding, right? So if you look at 6, 7, they're corresponding. Here's this 2, 3. So here, if you're trying to calculate, I think we would not be able to imply that this is congruent only because here's 2 and here's 3. So I think at the end, we would say that this is not congruent. And it's obviously because the SSS postulate does not occur because of the different values here and here. I think that's it. Also, when it comes to proofs, it's not really like about not just knowing the postulate, but I think that the only way you can be proficient isn't it is practice. So that's that. But the second part on proving triangles congruent by the SAS and HL. So note that here SAS is a postulate, and note here that HL is, on the other hand, a theorem. Let's look at the SAS. Like it's SAS, side angle side. When a side angle side of two triangles are congruent, then the two triangles are congruent. And note that here that the A angle must be included in the side. So it can't be like, for example, a side equal here, and an angle like here. It has to be such that it follows. So that's something to really remember about this SAS congruence postulate. So let's look at this proof really quickly. BC, we're given that BC and D are congruent, and the BC and AD are also parallel, and you're trying to prove the triangles are congruent, right? By the reflexive property, you can prove that they're equal to each other here. And this now all you need to prove is that an angle is congruent, right? But because you know from the alternate interior theorems, then you know that this angle and this angle will be congruent. And S side angle side here, same angle side. So that would be how you prove the postulate. Next is the HL theorem. We'll hear that the most important part of this is the fact that it's a theorem, not a postulate. But in addition to that, you probably all are familiar with the Pythagorean theorem. So a squared plus b squared equals c squared. And that, as you guys probably know, is only for right triangles, right? And then right triangle, the longest side is known as the hypotenuse. And this would be, in this case, AB, in this case, DE. And the legs would be any other side, so AC, CB, or DE, FE, right? So here, the HL theorem is, say, if one leg and the hypotenuse of two right triangles, and that this only works for a right triangle, are congruent, then the two triangles are also congruent. This is demonstrated really nicely here. So if you quickly look at this, let's see. You're given W at Y. Where's WY here? WY is congruent to XC. WZ is perpendicular to ZY. So this is this. And XY is to ZY. XY. And WY. Okay. And you're trying to prove that these two are congruent. So obviously, because you all can probably tell that these two angles are right triangles, because when you're perpendicular, that is 90 degrees, and that is literally the definition of a right triangle. So I think that's kind of just implied from the definition of perpendicular lines. EI also the definition of a right triangle. And next you can look, because you know that here Z y is equal to itself. So you could probably say something like, oops, cy is congruent to yz is to show the reflexive property, and that's how it proved your theorem, because you already know these two are congruent to each other, and that's good. That would be the hypotenuse, and all you need to do is the legs. So here you would do the legs. So I think this is a pretty simple proof in general, but if you, let's just do one last one before we end for today. So here, let's look at the SAS congruence postulate. So let's look at number 14. So you're given two triangles here, and you have to prove that they're congruent or not, but using the SAS. So here we already know that a side is equal. Another side that we can imply is equal is the shared angle, because of the reflexive property of congruence here. And this angle, and the final angle is the alternate interior theorems. We can also imply that these two angles are equal simply because of the given context. So, and this is also an included angle, so I think SAS would work in this case, and we can conclude that these two triangles are congruent at the end of the day. If let's just quickly look at number 21 finally. So Z is the midpoint of PY and XQ. So do you have enough information? So first you can know that these two are congruent from the vertical angles congruence theorem. And what else do you know here? Although, because you know that Z is a midpoint, then you can also know that these two angles are the same. This all applies for them. And I think this is enough evidence to use the SAS congruence theorem to prove that X, Y, Z, and P, Z, Q are congruent. So a final, let's try like a quick developing proof that comes here. So you know point M is a midpoint of Ln, and PMQ is an isosceles triangle. So remember that an isosceles triangle has the same sides like this, and the base here is PQ, so PQ is the only different side in this case. And Ln and angle L and angle N are right angles. So because these are the given factors, and you're trying to get to prove that these LMP and NMQ are congruent, you already know that the hypotenuses are equal simply because PMQ is an isosceles triangle, right? While the base is only the different one, so that's PQ. And the next thing you have to prove is one of these sides or here are congruent. And the way you can do this is pretty simple, by using the idea of a midpoint for Ln, because M is a midpoint, then you can imply that these two sides are equal. I think this is a pretty good explanation of the H-Hill theorem, and that would give your final answer. So just remember to review, and because this is a really important theorem that will be used really often in geometry, it's really good to know that. And next time we'll go more into learning about the ASA and AAS. Thank you guys, and great job today.